To show you how to find this in the table of values, you first want to go into y equals and type in the equation we have into the y1. We have x plus 2 over x minus 2 there. And now we want to set our table to ask, so we go second window and set the independent mode to ask. Once you've done that, you go second graph and it'll take you to the table of values. It's going to ask you to put in multiple numbers in order to find what the y value is at that x. So what I did here is I put in numbers that are getting increasingly close to 0, and we can see that in y1, the resultant numbers are getting increasingly close to -1. And that's how we know that the limit as it approaches 0 is -1. As mentioned previously when talking about left-hand and right-hand limits, there are cases in which limits can't exist. And we're going to be evaluating one of the situations where they can't exist, but there are multiple that we'll be going over later. So this situation is called piecewise functions, which is when you have a function with multiple equations within it to build that function. And as long as it passes the vertical line test and there are points which include and don't include in order to create a vertical line there, that means that the function can't exist. So here we have x squared minus 3 coming from the left and coming up to 1. And we know that it doesn't include 1 because we have x is smaller than 1, but there's no line under it saying that's including. That's the left side here. And on the right side, we have 3x plus 1, and we know that x is greater than or equal to 1. So it starts here, and we have the filled-in point coming up to the right. And we know this is a function because this one exists and this one doesn't exist at those specific points, therefore that the vertical line test works here. In order to show how left and right-hand limits don't exist here, we'll start here when the limit of 3x plus 1 as x approaches 1 from the positive direction. We used 3x plus 1 in this case because that's the right side of this function here. If we had a bunch of different functions, it would start to get a little bit more complicated, but as long as it works out in the end from the right and the left, it should generally make sense from those points. So we have the limit of 3x plus 1 as x approaches from the positive direction, and we simply just plug in 1 here. We don't have to do any sort of factoring in order to figure it out, and that just ends up being 4. We do the same thing with the left side, so the limit of x squared minus 3 as x approaches from the negative direction. We just plug in 1 and we get -2. We can see here that the limits are not the same. 4 and -2 are not the same number, and we can see clearly on the graph that they meet at 1 at different points. This proves that the left-hand limit and the right-hand limit are not the same, which means that the limit does not exist. Now that we've talked about piecewise functions and how that relates to left and right-hand limits, this leads straight into continuity versus discontinuity and how limits can't exist when a graph is discontinuous at a certain point.
Math is hard. Remember it was just 2 plus 2. Those are the good old days.
Actually, right now you guys are demonstrating perfect sharp transitions. So in the clip we just saw of Taylor on the farm running up this graph here, she immediately turns her direction and creates this sharp point on the graph. This is called a sharp transition, and this is one of the cases where there's discontinuity and the limit can't exist, because when it's going up, her slope is positive and it immediately turns to a negative slope. This is an issue later on when we have derivatives, and also with what we learned about tangent lines. If you find tangents, you're going to be getting different slopes at the same point, and that's pretty much impossible. So the limit can't exist because one slope is negative and one is positive. So in that clip we saw Emily running back and forth, and she suddenly came to a stop just because she was tired. But on the graph we see something very similar happening. So we have our function here, and it immediately stops. This can be due to restrictions or any other influence if there's a piecewise function and we just don't see the rest of it. But this is called an endpoint, and the limit can't exist here because there is no right-hand limit. There's nothing coming from that side, so there can't be a limit there. We just saw a clip of Taylor and Emily both running towards the fence, and Taylor here went towards and then down, and she got really close because she could never touch it. And Emily did the same thing, but she went all the way up. This is showing a vertical asymptote, and a vertical asymptote is both discontinuity and an example of when a limit can exist. And the limit can exist here because they're both approaching points and they're never going to reach them. And in limits, they never truly reach a point, but it's also the case of these are going to approach even the same y value if they were to be able to touch the vertical asymptote. I'm sure you guys remember first principles and how annoying it was to use, because if you had a really big function, you put it in there, it took you a really long time. So that's why we're going to be covering derivatives. And the derivatives is broken up to in a bunch of laws, which make it simple to find the derivatives. We're going to be starting with the most basic one, which is the power law. So in the power law, you have a coefficient and an x with an exponent. In order to find the derivative, you're going to be taking the exponent and minusing 1, and you take the original exponent and multiply it by the coefficient. And that sounds kind of complicated right now, so we have some simple equations to show that. We start with x to the 3. So first, you multiply your coefficient down. So we have the 3 go down, and the coefficient is just a 1. So it's 3x, and you minus the exponent by 1, get 3x squared. Same thing right here, except now we have actual coefficient that's greater than, we have 7 here. So we take the original 2 multiplied by the 7, and we get the 14 in front. And then you subtract 1 by the initial power, and you get x to the 1. And now this final one, it's a little bit different because we have a negative since there's a denominator. So we have our exponent in the bottom, x squared, and we just want to move that up to the top. It makes it a little bit simpler once you're multiplying things down. So we have 2x to the negative 2. You move your whole exponent down and multiply it by the coefficient, which is 2, including the negative. So we get negative 4x, and you take away 1 from the exponent. Except remember that this is negative, so you have negative 2 minus 1. Most people make the mistake and put negative 1, but it's actually negative 3. And you could just move it down. It won't really matter, but I like to move it down because you don't have any negatives. So you get 4 over x to the 3. Now that we've done the power law and understand derivatives, we're going to be moving on to something that's a little more complicated, but still pretty simple. So that's the product law here, and that's, you use it when you're multiplying two things that can't be combined and found the derivative of just on its own. So you turn it into two different segments, f and g, and you can put absolutely any letter. So f, in this case, is the first part of our equation, and g is the second part of the equation. Our equation is f derivative of g plus g derivative of f. This means that you take the first part and multiply it by the derivative of the second, and then the opposite for once you've added them together. So we have this equation here, 2x multiplied by 3x cubed. We separated it into these little housekeeping areas. We have f as 2x, and the derivative of f as 2. We just used the power law to find pretty much all of these. And g is 3x cubed, and g prime is 9x squared. Same thing, you took down the cube, you multiplied, and you subtracted the power by 1. Now you just substitute it right into the formula right here, and we get right here 2x times 9x squared. You can see I just took the f and the g prime just like that, and we did the opposite over here. We multiplied these in together in order to get 18x cubed, and we multiplied 3x cubed times 2 to get 6x cubed, and that ends up just being 24x cubed, and that's our final derivative. For this other one, it's a little bit more complicated, but it's the exact same process. We have 1 minus x squared times 2 minus x cubed, and we simplified these into our f and g and f prime and g prime once again. So we have 1 minus x squared and negative 2x, and also 2 minus x cubed and negative 3x squared. Once you plug these into the formula, it does look like a little bit daunting to have these all together, but we did the same thing as we did before, just multiplying them in. Make sure to watch for things like negative x squared times negative 3x cubed squared, because once you multiply them together, you get a positive, and if you don't put that in, you might get a completely different answer. Well, you will get a completely different answer, and that's not what we want. So we have the first time and the second time here, and you can just combine them all together at the end. Watch again here. I have a negative value, and it's adding it, so I just put a negative in there, or else I'm going to put a plus minus, and it's going to get really confusing, and I'll make mistakes. That's where a lot of people will make mistakes. Once you combine this all together, you get 5x to the 4 minus 3x squared minus 4x.